During the past century and a half, railways have developed to become mechanically the most efficient means of mass transport on land. But under certain track and operating conditions, some of the problems of rail transport attain serious proportions. On the 3-foot-6 gauge track of the South African railways, with curve radii as low as 120 meters and axle loads up to 18,5 tons, problems were encountered on both vehicle and track. Under these operating conditions, using vehicles fitted with conventional 3-piece bogies, excessive wheel tread and flange wear was encountered. Complementary track wear resulted. To overcome these problems, a novel wheel-set suspension system was developed, the Scheffel HS Bogie. The letters HS denote the two salient features of the bogie, high speed and high stability, but they are also the initials of its inventor, Herbert Scheffel.
In the late 60s, I was in charge of a design project to develop a new suspension for the new blue trains. The aim of the project was to find a suspension that would be suitable to operate at 120 kilometers per hour. In those days, the maximum speed operated on the South African Railways 3-foot-6 gauge was 90 kilometers per hour. We went overseas to study the suspensions in use on various high-speed trains on the continent and in the United States, and bought 6 different types of bogies, and we obtained an instrument coach and extensively tested these bogies under South African track conditions. The tests proved that with the bogies from overseas, a speed beyond 110 or maximum 120 kilometers per hour could not be obtained. Using mathematical models and computers proved that the reason for this was the hunting stability problem, and at the same time the South African Railways was embarking on higher axle load operation and longer trains to cope with the mineral traffic from Postmasburg, Sishen area, and later the coal traffic to Richards Bay. There, another problem occurred, and this was a problem of wheel wear and particularly flange wear.
To retrace Scheffel's work in the development of the new suspension system, it is necessary to understand the principles whereby a railway wheel set is guided on the track. A wheel set comprises 2 wheels rigidly connected on a common axle, with the treads of the wheels having a conical profile. While rolling in a curve, such a wheel set is displaced laterally with respect to the track so that the respective wheels contact the rails on differing rolling diameters. Forces are generated in the rail-wheel contact area, which cause the axle to align in the horizontal plane to a position radial to the curve. These forces are termed creep forces. These creep forces are generated whenever the wheel set is displaced laterally with respect to the track, or when the wheel set encounters a geometric discontinuity in the running profile of the rail. The resulting swerving motion is explained as follows. The creep forces between wheel and rail cause the wheel set to turn towards the center of the track, overshooting the center line and realigning itself to the track, but now displaced to the opposite side, in a position in which it has again to execute a centralizing motion. This repetitive action results in a periodic oscillatory motion, popularly referred to as hunting. The amplitude of the hunting motion increases until eventually limited by contact between flanges and rail. This compound motion involves the masses of axles and wheels, representing considerable momentum and energy which is derived from the traction power. It is capable of exciting all coupled masses, such as bogie frames and truck bodies, into related oscillations, which can feed inertial forces back to the wheel set, thus exciting even greater unstable motion. In his theoretical and practical investigations, Herbert Scheffel took into account that if a single wheel set could be coupled by means of springs to an infinite mass, the forces generated by the springs could counteract the creep forces and stabilize the wheel set. Such an infinite traveling mass, however, is not available in practice. In conventional bogies, this idealized model is approximated by using rigid longitudinal couplings between the wheel sets in the form of side frames. The result of this arrangement is that the bogie has to move over the track as a unit. Twisting or lateral movements are limited by clearance between rails and flanges, as shown here by flashed markers. On a straight track, the bogie hunts with a wavelength conforming to that of a single wheel set with reduced conicity. In a curve, the wheel sets are constrained to remain parallel to one another, and the flange of the leading wheel contacts the outer rail, and forces are generated to steer the bogie through the curve. These flange forces, coupled with resultant motions between wheel and rail, are the major causes of wheel and rail wear. This wheel has to be reprofiled after only 40,000 kilometers. Apart from the worn flange, the effective conicity, due to the hollow worn tread, has reduced the stability below that acceptable for the current operating speeds. Because both wheel tread and flange are worn, sufficient metal has also to be cut away to form a new flange. This means that wheel rims have to be made thick enough to withstand several reshaping operations, or else they have to be scrapped when worn. The factors causing wheel wear also have a detrimental effect on the track, which is more costly to repair. The lateral sliding motion of the wheel over the railhead on the inside of the curve causes metal flow. On the outer rail, the head is worn away by flange contact. In his efforts to find a closer approximation to the idealized model for stability, Scheffel considered that two wheel sets could be interconnected diagonally with rigid anchors and longitudinally by means of elastic couplings. The cross-coupling would force the axles to yaw in opposite directions on encountering a track irregularity. This activates the longitudinal elastic constraint in simulation of the elastic suspension to the infinite mass of the theoretical model. In turn, this arrangement gives the wheel sets the freedom to attain a radial position in a curve. In practice, the bogie is constructed by rigidly connecting a supplementary frame to the wheel set through the bearings. Diagonal coupling bars are then pin-jointed to this frame, thus allowing the wheel sets to yaw out of phase, thereby assuming non-parallel positions. The necessary elastic coupling is provided by two shear pads on either side of each bearing. The pads consist of alternate layers of rubber and steel. This construction ensures a high compression stiffness, but is designed for optimum shear stiffness and for the maximum deflections encountered in curves. The longitudinal elastic coupling between the wheel sets is completed through the side frames of the bogie. This shows the movement of an actual shear pad in a bogie running at 120 kilometers an hour. By comparing the even movement of the wheel with the movements of the shear pad, the function of the shear pad can be understood. The speed has now increased to 160 kilometers an hour, and the Scheffel HS bogie still shows no signs of instability, in comparison with a conventional bogie traveling at less than half the speed. The action of the cross anchors in a curve is demonstrated here. For the sake of clarity, the bogie frame is not shown. Because of the creep forces between rail and wheels, the axles are now aligned approximately towards the center of curvature of the track. A third feature of the Scheffel Bogie is the special Scheffel HS wheel profile. This was developed with properties to match the shear pad stiffness, ensuring adequate wheel diameter differential in curves, together with minimum contact stresses between wheels and rails. The excellent performance of the Scheffel HS Bogie is the result of meticulous research, engineering, and development. As such, it is much more than the application of novel mechanical arrangements. Through the use of mathematical models, computer verification, and empirical testing, the correct relationship between masses, forces, and other parameters was determined for the optimum functioning of the bogie. This scale model shows the physical construction of the Scheffel HS Bogie. Seen here are the wheel sets with subframes and with the cross anchors being placed into position. By putting the cross anchors in first, the articulation of the wheel sets can be shown. Two shear pads are mounted on either side of a saddle-shaped housing over the bearing. This ensures that the side frames will not tend to move about the axle ends with longitudinal movements of the wheel sets. With the fully assembled model, the articulation of the bogie is again demonstrated. The movement is now, however, restricted and restrained by the shear pads. The superior coasting ability of the Scheffel Bogie is demonstrated by the following test. Two wagons, each loaded to 80 tons, are allowed to run freely and uncoupled down a slope into a set of reverse curves. The leading wagon is fitted with Scheffel HS bogies and the trailing wagon with conventional bogies. At first they run together, but gradually the trailing wagon is retarded because of increased resistance in the curve as the result of flange rail friction. On entering the next curve, the second wagon is trailing further behind, whilst the leading wagon rolls smoothly through the curve. The wagon with conventional bogies cannot make it and grinds to a halt in the curve as the result of flange rail friction. As grades and curves tend to occur together, the layout of grades for a given traction power has to be compensated for flange drag in the curves. By using Scheffel bogies, costs are saved by laying out the line to steeper, uncompensated grades. By adapting the new suspension system to passenger vehicles, it is possible to increase the operating speed on narrow gauge track. A locomotive fitted with a nose cone to reduce wind resistance, a special gearbox, and a pantograph for high speeds was used for high-speed testing of a passenger coach equipped with Scheffel bogies. During test runs, speeds up to 245 kilometers an hour were reached. At these speeds, the Scheffel HS bogies were found to be perfectly stable, which in practice verified the theoretical predictions. Scheffel HS bogies are now in large-scale production. These bogies are being taken into service at a rate of more than 3,000 a year by the South African railways. Although the cross-anchor principle can be adapted to a wide variety of bogie frame designs, the South African railways opted for a design adapted to the three-piece bogies widely used in South Africa. The advantages of low cost, ease of manufacture, and excellent load equalizing characteristics of the three-piece bogie could be exploited in a simple design which added little to the mass and cost of the bogie. The cross anchors are positioned symmetrically between the subframes to obviate any possibility of a yawing movement being applied to the wheel sets during braking. During 1970, Scheffel HS bogies started rolling into the South African railways at a brisk pace. The first pressing need was to replace conventional bogies on the ore trains under 18.5 tons axle loads. By 1981, there were already 25,000 bogies in commercial service in South Africa and several other countries. The new suspension system has proved its worth wherever it was introduced. A striking example is this line where high-density chrome ore is hauled from low-lying river valleys onto the high plateau. Because of the uneven topography, the line goes through a seemingly endless succession of bends with radii as low as 120 meters. With axle loads of 18.5 tons, total wheel life was only 500,000 to 600,000 kilometers with conventional three-piece bogies fitted with multi-wear wheels. With the use of Scheffel bogies, it has increased to between 4 and 5 million kilometers with the same wheel. This is a 2-kilometer-long train carrying iron ore from Sishen to Saldanha Bay. The 864-kilometer line was specifically built for ore transport without sharp curves. Scheffel bogies have been in use on this line since its inception. By mid-1980, 100 million gross tons had been carried on the line. With axle loadings of 26 tons, wheel life with so-called two-wear wheels is 1,3 million kilometers. Minimum track wear was also experienced. Based on the experience gained on the Saldanha line, it has been decided to upgrade the track on the Richards Bay coal export line. Track engineers considered it feasible to increase axle loadings to 20 tons and later to 26 tons on condition that Scheffel HS bogies were used exclusively on the line. The Scheffel suspension also came into its own in this car carrier train. Motorcar loads are notorious for instability, caused by the high center of gravity, where the sprung masses of the cars tend to go into oscillation, in turn exciting the wagons into rolling and nosing. 400 cars are carried at speeds of 75 kilometers an hour or more without any instability problems. Wheels in this service have already exceeded more than 1 million kilometers without reprofiling. The advent of the Scheffel HS bogie has heralded a new era in South African rail transport. In the future upgrading of all types of services, the superior performance of the new suspension system will play an overriding role because of the wide spectrum of advantages to be gained from its use, such as lower maintenance, no flange wear, low tread wear, low track wear, low bogie maintenance, increased revenue, higher operating speed, higher axle loads, cheaper line construction, energy saving in curves.